Today we are going to continue looking at verifying trig identities. I'm going to show you a few more strategies for verifying identities. First, we have secant alpha plus tangent alpha equals cosine alpha over 1 minus sine alpha. I'm going to show you two different ways to do this. One by simplifying the left side, the other by simplifying the right side, but they both use the same new technique. So first, I'm going to start on the left side. I have secant alpha plus tangent alpha. I'm going to rewrite this in terms of sine and cosine. So I have 1 over cosine alpha plus sine alpha over cosine alpha. Since both of these fractions have the same denominator, I can go ahead and add them together. So I have 1 plus sine alpha over cosine alpha. Here's where the new thing comes in. We are going to multiply by the conjugate. If you remember, the conjugate of 1 plus sine alpha is going to be 1 minus sine alpha. And I need to multiply on the numerator and denominator. So, for 1 plus sine alpha and 1 minus sine alpha, you can FOIL or double distribute, but because they are conjugates, the middle terms will end up canceling out and you just have 1 minus sine squared of alpha over, I'm going to leave this as cosine alpha times 1 minus sine of alpha. Then by my Pythagorean identities, I know that 1 minus sine squared of alpha is cosine squared of alpha. Then I can cancel cosine of alpha with one of these cosine of alphas, and I'm just left with cosine of alpha over 1 minus sine of alpha, which is what we wanted. Now, you can use the same multiplying by the conjugate technique to do this by simplifying the right side. So, if I decided to start on the right-hand side, I would start by immediately multiplying by the conjugate. So I would want to multiply by 1 plus sine of alpha over 1 plus sine of alpha. My numerator I'm going to leave as cosine alpha, 1 plus sine of alpha. The denominator, if you multiply these together, you get 1 minus sine squared alpha. Now, by using my Pythagorean identities, I can change 1 minus sine squared of alpha to cosine squared alpha. And then I can cancel cosine of alpha with one of these cosine of alphas. Now, I can split up my fraction and have 1 over cosine of alpha plus sine of alpha over cosine of alpha. And then I can simplify these. 1 over cosine of alpha is secant of alpha, and sine alpha over cosine alpha is tangent alpha, which is the left side of the problem that we started with. So it doesn't matter which side you choose to simplify. In some cases, one is easier than the other, but either one will work. Let's take a look at a second example. Here I have sine cubed x times cosine to the fourth x equals cosine to the fourth x minus cosine to the sixth x times sine. So I'm going to start working on the left side of this problem. And I'm going to split up this sine cubed of x. So I have sine of x times sine squared of x times cosine to the fourth of x. By my Pythagorean identities, I know that sine squared of x is 1 minus cosine squared of x. Then I can go ahead and distribute the cosine to the fourth of x. And then I just switch this around because multiplication is commutative, and I have cosine to the fourth x minus cosine to the sixth x times sine of x. If we had decided to start with the right-hand side of the problem, we can do the same type of thing. If I start with the right, I'm going to factor out a GCF of cosine to the fourth of x. Then I'm left with 1 minus cosine squared of x times sine of x. By the Pythagorean identities, I know that 1 minus cosine squared x is sine squared x. Then I can multiply the sines together, and I get sine cubed of x times cosine to the fourth of x. So you can choose to simplify either side of the identity. It does not matter. Let's look at one more problem, and I'm going to show you 3 different ways to verify the identity. We have cotangent squared of theta over 1 plus cosecant theta equals 1 minus sine theta over sine theta. So the first method I'm going to show you, I'm going to call the Pythagorean way, because I'm going to start by using the Pythagorean identity. I'm going to work on the left-hand side. I know that cotangent squared of theta is cosecant squared of theta minus 1. Now, in the numerator, I have a difference of squares, so I'm going to go ahead and factor and get cosecant of theta plus 1 and cosecant theta minus 1. Now, I can cancel out cosecant theta plus 1, and I'm just left with cosecant theta minus 1. Well, I know that cosecant of theta is 1 over sine of theta minus 1. Now I need to get a common denominator, so I'm going to multiply this 1 by sine theta over sine theta. So I have 1 over sine theta minus sine theta over sine theta, which gives me 1 minus sine theta over sine theta. And that's it. But that's not the only way I could do this problem. So let's look at the same problem, and I'm going to show you how to do this using conjugates. So I'm going to start by multiplying the left-hand side by the conjugate 1 minus cosecant theta. So in the numerator, I'm going to leave it as 1 minus cosecant theta times cotangent squared theta. In the denominator, if I multiply these together, I get 1 minus cosecant squared theta. Well, 1 minus cosecant squared theta is very close to a Pythagorean identity, and it is actually the negation of the Pythagorean identity, meaning that the signs are all switched. So 1 minus cosecant squared theta is the same as negative cotangent squared theta. So then the cotangent squared thetas cancel out. So I have 1 minus cosecant theta divided by negative 1, which gives me cosecant theta minus 1. And then I do the same thing that I did on the previous version. I'm going to change this to 1 over sine theta. Then I need a common denominator. And I have 1 minus sine of theta over sine of theta. And I'm done. Let's look at one last way to do this problem. I'm going to call this the sine and cosine method. So far, you all have a tendency to change everything so that it is in terms of sine and cosine. You can do it that way, but sometimes it's a little bit more complicated. So let's take a look at what happens on this problem. I'm going to start by changing the left-hand side of this identity so that everything is in terms of sine and cosine. So cotangent squared theta is cosine squared theta over sine squared theta. And 1 plus cosecant theta is 1 plus 1 over sine theta. So the first thing I want to do is get a common denominator here. So I'm going to multiply by sine theta over sine theta. I'm going to keep the numerator the same. And in the denominator, I have sine theta plus 1 over sine theta. So now I have a fraction divided by a fraction, so I need to multiply by the reciprocal. So I have cosine squared theta over sine squared theta times sine theta over sine theta plus 1. This sine theta cancels with one of these sine thetas. So now I have cosine squared theta over sine theta times sine theta plus 1. I'm going to go ahead and use Pythagorean identity on the numerator here and change cosine squared theta to 1 minus sine squared theta. Then I'm going to factor the numerator. This is the difference of perfect squares, so I have 1 plus sine of theta and 1 minus sine of theta. Then the 1 plus sine thetas cancel out, and we are left with 1 minus sine of theta over sine, which is what we want. As you can see, this approach is a little more complicated. It works, but one of the previous two methods is probably easier. So don't get stuck in a rut of always changing to sines and cosines, because frequently there is another approach that is much more efficient.